I would like to leave you in the very capable hands of Cauê and Napier, who will be talking about concept designs and trade-offs.
Thank you, Andy. So let me just set up everything and start sharing my screen. If you can confirm that you're seeing my presentation, I can
Yeah, I'm
just
seeing it.
start it. All right. So yeah, welcome everyone. Nice to talk with you again. And well, today I won't be actually teaching design studies and how to do exactly all the conceptual things behind it. There is a lot of books, and this is a whole university class or even a course on that. So today we're going to raise and discuss a bit on the key practices and things to remember and to think about before and during your studies. And whoops, and this is mostly a collected of practical wisdom, as it was on the first webinar. This is things that we currently discuss. We usually discuss with customers and see the usefulness of it. Don't take it as purely the truth, the main truth. At the end, you always will need to think for yourself and see how that applies to your system or to your project. So take everything with a grain of salt, but have those questions always coming back to your mind when you're going through this process. So in general, the topics or the flow that we are going to go through today, as many of you mentioned, stakeholder needs or requirements is one of the main things. So we start with our defining why do we actually need the system, right? So after we have discussed all the stakeholder needs, we can move to defining a solution neutral function. So clearly define with all your team what will the system do and try to be, as the name say, as neutral as possible before defining something specific. When you have that agreed with your entire team and also stakeholders, you can move to concept design. So the first step on how will the system do it. So it will be the initial level. Then you can move to actual architecture definition. So defining how the system will emerge out of all those functions and subsystems. Just to recap a little bit, we will keep using as example the Valispace that we presented last month. So the Valispace is electric powered human transport. So as you can see on this image, we already have this concept already well defined with a nice picture, but we need to take several steps back to actually question what we're doing here for that system. And then the question comes, why design studies and concept analysis? Innovations exist in the unexplored trade space. So don't be afraid to actually take one step back before committing to a given solution. Talking with many engineers, we always see that people are locked on a specific solution, and the specialists, the engineers that are developing the subsystem, don't really understand why those solutions were taken in the first place. And when performing concept analysis, you and your team will have a better understanding of the dependencies and impact of each design solution. That will help you take better decisions, smarter decisions, which will consequently help you to also better manage complexity of your system. So you understand more how things impact each other. And also grow your system from a simple system to a complex system instead of diving directly to a really complex system, especially when you start modeling. Don't be afraid to take one step back. I know that especially for startups, we are all rushing to get to the latest version and release it to our customers. But taking one step back won't cost you too much at the beginning and probably will save you a lot of time and headache in the future. So to first start with the stakeholder needs. Why do we need this system? Clearly understand what needs to be accomplished without ambiguity and have all your team on the same page. A couple of times talking with customers, especially when have a bigger team, you see internal discussions of people, which is not super clear what's the main point to be accomplished. And choosing the right problem statement it's a really big important step. So, for example, defining a public transport that transport people quickly and more efficiently is a much better scope than making a more powerful bus. So think about the problem statement before just diving in on your system definition. And projects tend to be more defined and have a better start when the system architects are involved on the upstream processes. Do not separate commercial and strategical decisions to the technical perspective. Those two, like the system architect, will bring much more knowledge on how to implement things, and most of the times, customers just come with a given defined solution, right? And the system architect should also be able to question some, not all, but some of the stakeholder needs. So for example, the helicopter that we see, we already talking about electrical vehicle, but why exactly are we going for the electric vehicle? And some of those questions might be necessary to be done early on. And remember to register all the discussions and all the rationale behind all the stakeholder needs. They might come handy in future. And as I mentioned, we've already talked with engineers that don't have it clear why specific solutions were taken or specific decisions were taken regarding architecture. So having a good not repository, but a good log of all that discussion, it's a good tool to have on your process. Going back to last month webinar where we talked about the customer specifications for the Helicopter, if we review the really high level customer specification we received, we see that there is a couple of architecture decisions locked in. So the first point is really well defined. You see that it needs to transport 4 passengers within 15 minutes with that distance and that price. So it is something that commercially someone did an analysis. So it's always good to have that analysis easily available for every engineer. But I would question the 2 other points. So the second point directly implies a solution. It doesn't explain why we are choosing electrically. So what's the main target? What's the reasoning behind it? Do we aim for flight costs, for system costs, efficiency, maybe noise and pollution? So it's always good to question that back. And the second one as well. Well, the first part is okay. This should be splitted, but the first part say about the size that have a clear reasoning, but that it should fly autonomously. Again, the system engineer or the system architect should be available to discuss the rationale behind it, to think about the regulation. Are we there yet already? When we release this project, will the regulation allow us to have a fully autonomous flight or not? Or are we choosing autonomously for safety, for cost, and so on? So have a system or have on your process all that discussion so you can take better decisions instead of basing on something that wasn't thought well. Well, after going through all your stakeholder needs, then we can start talking about actual defining the function of the system. And we always ask for customers and always talk with engineers to come up with solution neutral function. So what the difference between more solution neutral and less solution neutral? When you need to explore new markets or new solutions, go for a more solution neutral. As I said, we want to transport a person from point A to point B inside a city, instead of we're developing a quadcopter electrically and autonomously. Yeah, and don't be afraid again to ask what the customer is asking for. Most of the times, they really come with a given solution instead of defining the problem itself. But if it is strategically clear that you're going to explore an existing market, that your company maybe is already part of that market, you can move to a less solution neutral function definition for your system, but always try to be more solution neutral when developing the subsystems. So how actually our electric vehicle is going to perform, make that step back to go to a less, for more solution neutral. As I gave the example, the main or the most solution neutral function of the Valispace is actually to transport people from A to B inside a city within a given parameter. While a much less solution neutral is actually electric in-city aerial vehicle. After agreeing with the stakeholders, with all the architects and the company strategy, we can agree on the system function and then start working on the actual design of our system. So we go to the concept design, how the system will do it. So just to first start defining the wording here, sometimes people mix between concept and architecture, but we first start with the concept design, which is a really high level mapping of form into function. So how my overall system will do and what's the minimal part that we needed. So defining the minimal mapping of the internal operations of your system. While later on, after defining the concept, we can move to an architecture, which is already a complete decomposition of function and form of your system and includes all the iteration and supporting processes of that system. So if we start with a concept definition of the Valispace with a functional analysis, for example, we can define that those are the minimal functions that we need to execute that main function. We need a supporting system, a propelling system. They could be the same or not, but you need to break down the minimal functions as much as you can. Controlling, storing energy, guiding, and accommodating passengers. So those are the main functions. And spending some time into understanding what the main functions will help you grow on your system later on. So after clarifying all your system functions on that level, that allows your system to emerge, the main system function to emerge, map all your concept alternatives and the rationale behind it. So what are all the options, what is it impacting, and so on. While mapping all the function, all the alternatives, please think about the entire life cycle of your project. Think about the manufacture, integration, operation, and also disposal. We see more often than not that some of these phases are neglected, especially on the initial concept design. And you might pay later on by redesigning parts of your system because you didn't take into consideration integration sometimes is well neglected. And time spent on representation of your system has been proven to be time well invested. It will help you and all your team to manage and communicate the system complexity. And then later on, specialists and analysts, they will have a better visibility of your system concept and all the architecture decision and all the impacts of those decisions. And like representation, modeling invested early should also support your test concepts. Just don't forget to track all the simplifications that you did along the way, but start modeling early to see which option looks better or have more impact on your main parameters. And a good tool on whatever process you're using, it will support you registering all the process. And if you don't have a specific tool for that, I mean, even a simple document where you log all your process, all the decisions and all the assumptions you're taking along the way, it shows to be really helpful. I've seen already customers using Valispace, using the documentation part of it to actually have the discussion as a document, like we're taking the decision because of that. Those are the assumptions, or those are possible impacts of that alternatives. Later on, this helps a lot to engineers when they start working on the more complex designs. So if we go to the Valispace, we see a simple definition of some of the alternatives we have for the concept design. But before defining all those alternatives of your system, think about what each function determines and also the possible dependencies. So if we go here, for example, the support and lifting will determine the flight envelope, the performance, the propelling will probably determine the noise level, the efficiency of the flight parameters, while the controlling will determine reliability, have a big impact from coming from regulation. The storing energy will have a strong influence on the range, on the cost and efficiency of the flight, as well as a big impact on the pollution levels. And guiding will also impact, for example, the agility of the overall platform of the Valispace. So again, having that clear and that agree with your team and thought before selecting something will help you make better decisions. But after having all those alternatives, so here in Valispace, we have, for example, for supporting, it could be either a propeller or a wing. For propelling, it could be the propeller or a jet. So if we select, for example, a wing and a jet, we're probably just doing an airplane. But you can play out with all that alternatives and see how combining different alternatives will help you design a better system. But after having all that alternative listened, don't just start picking them randomly, because it might be difficult to see what decisions you should take first, like what has the biggest impact. And this is one methodology to have to help you decide which alternatives you should select. You can just define all your alternatives according to their sensitivity and connectivity. Sensitivity are, well, highly sensitive decisions have a strong influence on the metrics of the system. So in this case, like the flight parameters or the cost of the flight. While highly connected decisions, it's how connected with other decisions it is. So how much rework you need to do in case you change that decision. So I would first start with the first quarter for highly sensitive and strongly connected, then move to the first quarter that are sensitive but weakly connected. So for them to move to insensitive and strongly connected alternative, and always leave the fourth, the less connected and less sensitive questions for decisions for later on. Going back to the Valispace example, you need to do some important analysis on all that questions, but to give this example here, we can define that the proportion type is something that is highly sensitive and highly connected because it will impact all my flight parameters and efficiency and cost and so on, but it's also highly connected because changing the proportion type will change all my structures and how we are going to allocate certain systems or certain elements, and will impact also on my control and so on. The decision between a fixed or a tilt rotor, so how you're actually going to maneuver the Valispace, it is highly sensitive because it will impact on all the agility and performance of the system, but it doesn't have a really big impact on other subsystems. While on the decision between autonomous and crewed flight, it might not have too much. This can be argued, this can be discussed, but overall it doesn't have, it's not too sensitive because it will not impact my overall system parameters, but it's definitely highly connected because you need to define all the control, all the support system for the crew and all of that. While lastly, for example, a fuselage material will probably impact the mass, which will impact the flight parameters, but it doesn't have impact across the range of my system parameters. And it's not too connected either to other decisions. So allocating all of that will help you take in better decisions first before just diving in and locking into a specific solution that later on might give you some headache. So after having these initial concepts defined and all the options, you can start expanding your architecture definition. That's where we go to the fourth part of the architecture. So how does the system emerge and how is the internal processes happening on my system? We've seen many times talking with customers that a clear decomposition and talking early about how you're going to decompose your system helps to manage the system definition and also to communicate that between your team. So make sure to invest some time on that process early. And distinguish between primary and secondary value and track the relationship, because engineers don't always know what is the primary and the secondary function of your system. So just to explain, to be clear, secondary values functions are functions that they are required, but they are not the main function of the system. So for example, the Valispace, it is to transport people, but an AC, air conditioning, might be a secondary function because this is a requirement for our customers. But this decision shouldn't impact any performance of the primary function. If the secondary function is impacting anything on primary, you should reevaluate either how you're decomposing your system, or if that actual secondary value is necessary or can be negotiated. And when performing system decomposition, especially on functional analysis, focus on reducing interactions and simplifying interfaces. There are several methods or several discussions on that topic. We talked a lot about a design structure matrix, where you can just define all your functions on a matrix, and you will have the dependencies of each function to each other, and you can use algorithms to group all those functionalities to make every subsystem as independent as possible. This is a really big topic to talk. We won't have time to talk about it here, but I recommend investing some time on it too. And another methodology that is quite powerful is to go the two down, one up when decomposing your system. So where you define two levels of your system, and then you go back one level to review if all the functions are being fulfilled, if all the interactions are already defined or not, and see if you're missing up something. So every time you go on, you are defining the next level, you define two levels directly and then go one up to review them. Just for a simple example here, the Valispace, we have the main system decomposition, and the selections are ready for the lifting and propelling. We have the propellers, and we can define the lower levels. So for performing this main function, we need three other functions in general. We can decompose it a bit more, but for this example, we need one to generate thrust, other to rotate propeller to redirect it. To generate to support generating the thrust, and another function to actually regulate the motor. And you have those system broken down. And on the process of defining this second layer of functionality, you will see if all the definition of the first level is well defined or not. Yeah, and after performing your system definition, you have a better understanding of all your possible solutions, and you can start modeling your system. So models are generated to answer questions. Know what needs to be answered. Always have in mind, before start just modeling, start calculating everything, know what is the question that you need to answer. Have that clear from the first point. And best models make evident how their outputs will be used in decision making. So again, talking with stakeholders or talking with the system architect before modeling, because those outputs should be the focus of your modeling, for not wasting time or not getting distracted with other alternatives. I don't know how you're performing all your models and how you're developing them, but it is quite important. It is super important to have your models connected with your system definition. And that's why we always talk about single source of truth and single repository, because if you have first an Excel spreadsheet that you're just calculating a basic function, you have a Simulink model that has all your dynamics of your system, and you might have CAD models. If they are not connected with your system definition, you might lose track of how things are evolving. And at the end, all your different models, they should agree with each other. So they should always be referencing to the same. You should be talking about the same system instead of having different kinds of systems all over your model tools. And when you have that connection between different levels of complexity as well, you can always go back to review a specific option. For example, you might have I mentioned that before, but you might have at the beginning a simple equation that just calculates the range of the airplane, and later on you might have the Simulink model. if you update the wing size of your airplane or the size of the wheels of your car, you should step back, especially when you're making big decisions, should step back to your simplified models and see if all of that's still valid before moving forward, and just keep working on a way too complex model where you might lose track of some important assumptions. And a reminder, account for uncertainties on all your trades. When you're doing trades, some systems might have already been developed, so you know more how the performance is or the main parameters, and other alternatives, you don't actually know how it will actuate. If you're trading between these two options, make sure to account uncertainties and all the margins. Make sure to have that on your tools, on your models, because some cases people take a decision based on unknown uncertainties, and that will give you a lot of headache. Also, test early decisions ideas with your simplified models, but never forget about all that simplifications, especially if you're, for example, if you're modeling a car, it's okay to assume that Earth is flat, but if you're modeling a rocket, you might start with a flat Earth, but if you keep that later on and you forget about it, somehow on your simple calculation, you might have some problems. So in every step, make the exercise to list all your assumptions. Sometimes, especially when working with complex Simulink models, you might have so much layers that some layers are neglected and people don't go back because nobody feels responsible for it. So always assigning ownership for the models and also the subsystems, the submodels, it's an important step. And that's also part of the main topic. The main point of this slide is for having a clear understanding between all decision makers and all the analysts for your model. What's the currently understanding about the system? Do we know exactly how the system will behave or not? Are we taking also simplifications on how the system behave? What, as I said, what are the key assumptions and the possible impacts? So at initial phase, it might be okay to take assumption, but think ahead what this assumption will imply later on. And if your platform can, leave reminders or leave some important flag that this should be reviewed at phase B or C, for example. Dynamics and behavior simplifications often happen at the beginning. Make sure to review them, especially when you're trading off between different alternatives. Different alternatives have different behaviors, so keep track and all of that well documented. And one thing that is important to discuss, because mostly this discussion is neglected, is that young engineers tend to overtrust models, while most senior engineers tend to ignore really complex models. So neither, well, it always depends on the state of the phase or of the project and how the model is performed. But have this discussion of what's the credibility of your model and the reliability of that. So don't skip that discussion. Never on any phase of your project. And yep, for concluding, those are the main process we've discussed. So stakeholder needs, clarify all stakeholder needs and don't be afraid to negotiate it, especially having the architects involved on it. Talk about solution neutral function. Don't dive a red directly to a specific solution. Make sure to explore the trade space or open it for allowing you to explore it later on. For the concept design, understand and test all your options before selecting. Never lock in on something before you understand how it will work and before having clear what might come in the future. This will all come with experience, with knowledge, but make the exercise of thinking how this will be down the road when you're modeling or when you're architecting your system. And finally, for architecture definition, invest early to save later, especially document the process. Talking with a lot of customers, we see that customers that have all the process documented, even if it is just a journal, help them going through difficult decisions or defining better solutions for the complex systems. Well, and that's it for the topic today. I hope those are some important questions that you might take later on your discussions inside your processes. It is a big discussion to have all around that topic, so feel free to just write either a question or a point that you have on some of those questions going back to hot slides, and I'll be happy to discuss that either now if we have time or just going into some one-on-one discussions later.
Cool, Cauê. Thanks very much, Cauê. That was really nice. I think you shared at the start that you could have whole university modules dedicated to this kind of topic. Yeah. So thanks for a nice overview of just the critical concepts to do with concept designs and designing a system architecture. I think that was very clear. I don't know if you can see on my screen, there's some questions here.
Yeah, I will go for the last one because it's the quick one and quite so could you define what's more sensitivity? So sensitivity is how a decision will impact the main, to use the wording here, the main KPIs of your system. So if you are developing a system, let's see, if you are developing a car that needs to go from point A to point B the fastest possible, all the solutions that will impact on the speed of your car is highly sensitive. And other options that might be a secondary impact might not be so sensitive. I hope that answers or define better the question.
So in a sense, you're saying that you define your own sensitivity from the start of the project?
Yeah, for every, it's important to categorize or to define sensitivity and connectivity for every alternative or every solution that you have on your system. Yeah.
And maybe that answer leads into the top question,
yep,
which is, can key performance indicators be defined as too subjective? What's the best way to define KPIs to undergo trade-offs?
Yeah, KPIs, they shouldn't be too subjective. They should be clear. They should be easily measurable, especially avoid compound KPIs or something like user satisfaction or user comfort. User comfort, if we're talking about flying vehicles, for example, you can then go to maximum acceleration or vibrations and things like this, but don't be too subjective or too I am, as an engineer, and most of us, I think we would go for numerical KPIs, right? Not something that is too generic. Sometimes it's a bit difficult to avoid them, but yeah, once you have your KPI defined, especially when you see, for example, the time it will take for a specific mission or the efficiency of that system, you can just every time that you will do a trade-off analysis, you need to have those KPIs on top of your list. Like, this is the thing that we need to compare doing the trade-off. And it's also important to rank those KPIs because maybe cost is as I said, is a secondary one. So if you can, a simple table where you define all the KPIs and see how each trade or how each alternative is impacting the KPI, it's helpful. I hope that that goes to the point that you wanted to raise. I don't know if I was too subjective on my answer, but
yep. And of course, feel free to do follow-up questions at outsites.com/Valispace if you would like Cauê to re-clarify what has been said. Maybe we can answer Sajad's question, which is, how do you cope with sensitivity analysis for driver requirements, mainly when you have problems with budgets like mass or power?
I'm not sure if I got the main point you want to uncover here. How do you cope with sensitivity analysis for driver requirements? Mainly when you have problems with budgets like mass and power.
Sajad, feel free to re-clarify your question in our site if you'd like.
or it can be also in Zoho if you just don't want to write a new question. We can take a look.
Yeah.
But I would go back to one, define what is the main driver. Because, for example, if you are struggling between mass and power, you have a system that if you increase, you don't know which one you should prioritize. One alternative that I like to see is always see the actual mathematical dependency or impact of those. You probably need more power for the system, which will drive the mass. So if you need more power but you're already over budget on the mass, don't be afraid to go back to the main requirements or to the stakeholder needs, because most of times you come to a dead end road that you need to renegotiate some things, and that will be the paper of the system engineer or the system architect, is to at the end have a final decision of what should be prioritized or not, or again, maybe exploring the trade space to find other alternatives or other solutions instead of fixing something if you go into a dead end.
Okay.
So we have a map between the system specification. It may have different.
So maybe we'll go to the next question, which is, along a whole concept design workflow, how much is it important by your experience/opinion a right balance between improvisation stages and more structured phases in order to use creativity properly?
Yeah, I love that that sentence or that question. I don't think that when you're engineering, you should improvise too much, but not killing creativity. I don't remember. I don't remember. There is a quote, I think, from Dali. I don't remember exactly, but the main idea is that if you don't have a canvas, you can paint. So you need to have a canvas. You need to have a scope to paint on it. That's why I was focusing too much at the beginning to think about the needs, to think about the solution neutral, and that's where the improvisation or the creativity can emerge, is allowed to flow. But the process, the phases, I think it should be structured. The structure is there to hold you, for you not to fall on some common mistakes, and leave that space for improvisation and creativity on those areas where it's usually neglected. I see it very often, or we don't hear too much people discussing that in industry in general. Okay, there are some comments on Zoho here. You got a point that I want to ask, but notice how you model the system for managing high number of changes, which may lead to changes in requirements that you need to negotiate. Yeah, so having a system, or and this is where Valispace comes, or this is one of the main points that Valispace tries to solve. Just to try to rephrase the message for the ones that are not reading the question, it's how do you manage this high number of changes and complexity of your system, which might triggers a change in requirements and change in requirements that you need to negotiate with the customer or the stakeholder. That's why tracing everything, having a clear trace, like what drives what drives what, will help you later. Bidirectional tracing, by the way, will help you later on to go back and see, okay, these really small, silly selection that we're doing at the end road that you can see on your system is actually impacting that main requirement for the customer. So having clear, and that's one of the points that I was talking also on the primary and secondary function values. Have clear which is actually secondary or not. How do you efficiently deal with the propagation of trade-offs? The trade space normally don't cover this. The trade spaces don't. So one of the the approaches in Valispace for propagation of trade-offs is when you're performing the trade-off, you define your alternative spaces. So for example, the propulsion type, it can be either electric or chemical or nuclear. You define that as one subsystem. And then all the alternatives will be, well, that subsystem will be a placeholder, so it will be a common reference for outside. So you treat that as a black box that you can just switch the black box, but all the interfaces of all those alternatives will be the same. So when you're doing the trade-off between electric engine and combustion engine, you need to have common parameters going out of either the alternatives. So probably not fuel consumption, because fuel consumption is something specific for the combustion. However, the efficiency might be something important, or the final mass, because when you have propellant, you have an extra mass that you have on the battery, but which is a varying mass. So I think I'm digressing here, but the main idea for dealing with propagation of trade-offs is to do the trade-offs within a black box. So, and have common interfaces between all alternatives. Whenever you're trying it out, all the options should have the same output, or the same, not the same answer, but the same output.
Great. Cauê, I think that's going to have to wrap up the question part. I hope everybody had their questions answered. And of course, if not, and you do need some more clarification, then feel free to reach out. Solutions@valispace.com. Find us on our website. And before we leave you, I just would like to say that today's webinar, I think you would agree, Cauê, was mostly about the theory. And if you did want to find out how this is done in a practical setting, then in tomorrow's webinar with Cauê again, we'll be showing you how it's done in Valispace, which is, as I said earlier, a digital productivity tool for engineers that are working in complex hardware. And I think that we'll be going through and showing you in detail exactly how this is done on a digital tool like Valispace, and going through some of the concepts that we did touch on today. But I'm also really curious into what kind of topics that you would like to hear from next to do with the rules of engineering. As I shared with you in the past from our old webinars, some people at this point have mentioned that they would like to hear about design concept studies and trade-offs, hence here why we're here now. So if there is anything that you would like us to cover, then mention this in ahaslides.com/Valispace. And we do take note of these, and the wizards in the back end are always deciding which topic that we should be focusing on next. So I can see here decision propagation. That's something to think about, Cauê. And even if this is the only thing that's here, I think that's still interesting enough. Testing and verification. Well, it's very interesting that you say this, actually, because in our next webinar, the Valispace Live 3, that's taking place in June, which is a month away, which itself is crazy enough, we'll be exploring how to do verifications and tests, kind of going off or continuing from the first Valispace Live, where we talked about requirements. Now it's about verifying them and testing. And in the day after, we'll be telling you how this is done in Valispace's testing module, which is a super powerful module where tests and simulations can be done. And we'll be taking a deep dive and a demo in there. And I'm sure Cauê will have his hand in this webinar again. And that's that. And I would like to thank all of you for participating. I hope that you've learned, you've taken something away. And if you're curious to learn more, then please join us for tomorrow's webinar. You can find this on the research and webinars page on our website itself, which is in the footer. You can find it across our social media channels. And then if you did just want us to review your own requirements process, think about how Valispace or a digital tool can work in your own bespoke company or processes, then please reach out to us at solutions@valispace.com or wherever else you might find us. And we'd really, really like to hear from you. So apart from that, I hope you have a super productive week. I'd like to thank Cauê as well for preparation and presentation. And yeah, have a nice week. Take care.
Thank you very much, everyone. Take care.
Thank you, everyone.